Hello everyone. Today we have a talk by Aitor Sanchez, a new deep learner in the group. And it's called Self-Supervised Anomaly Detection in Time Series. So Aitor, good luck.
Thank you, Andoni, and thank you all for coming. This time I'm going to make a brief introduction to my PhD thesis, which is based on using self-supervised learning for performing anomaly detection in time series domain. So, first of all, for the people who are not related with this field, I'm going to make a little introduction about the task of anomaly detection in time series by explaining different kinds of anomalies in this domain, different state-of-the-art approaches for detecting them, and afterwards I will go on with one of the main topics of my thesis, which is using self-supervised learning as a new unsupervised methodology in the field of machine learning, and how this can be applied to the task of anomaly detection in time series. And finally, I will tell you a little bit about the work that we are carrying out currently, and that's it. So, we define a time series as a collection of different measurements or recordings that describe the behavior of a system or entity in a certain period of time. So, depending on the number of dimensions that we are analyzing, if we are analyzing the evolution of a single variable over time, we say that we are analyzing a univariate time series, for example, in the case of an electrocardiogram. In other cases, if we are analyzing different univariate time series that jointly describe the behavior of a single system, we say that we are facing a multivariate time series. For example, in the case of a complex network in the Internet of Things field, in which we have different measurements according to different sensors that describe the behavior of a single system. So, what are anomalies in time series data? This is a really intuitive question and simple to ask, but it's not easy to answer. Why? Because depending on the context of the system that we are analyzing, we can find so different kinds of anomalies. For example, if we are analyzing the evolution of the expenses of my credit card over a certain period of time, if Lozano steals my credit card and he decides to buy a car, surely, as this is not a regular expense in my daily life at least, there will be a point in time describing that expense which deviates from the normality of the evolution of my expenses, and this is the example of a point outlier in time series data. If we move on to another context, for example, if we are analyzing the water consumption of the people who live in a particular city, if a leakage appears in the water distribution system of that city, since the leakage appears until the leakage is fixed, the time series that describes the water consumption of the people that live in that particular city will be higher than expected. So this is the example of a subsequence outlier. And finally, if we move on to another context, for example, if we go to the Internet of Things field in which we have a complex network, a system based on different sensor measurements, imagine that we have different univariate time series describing different activities of that network. For example, here we have variable 1, 2, and 3, which are recording normal activity, and they are so correlated, they are having like regular measurements, and suddenly we have variable 4, which corresponds to the fourth sensor, which is recording abnormal activity. So here we have, for example, an outlier, a complete outlier univariate time series within our more complex multivariate time series that describes our Internet of Things network. So as you can see, there are so different kinds of anomalies depending on the context that we are analyzing, and it's not easy, it's not trivial to find a general definition that includes all these cases. But at least we can say that anomalies in time series data are abnormal events which are not likely to happen, and in every case when they happen for a certain period of time, the behavior of the system that we are analyzing deviates from the normality that we expect, and therefore this system shows different patterns or characteristics that we cannot see under normal conditions. So the task of anomaly detection is based on identifying this kind of abnormal events as soon as possible in order to fix them as soon as possible as well. So in the field of machine learning, we have different approaches for tackling this problem. We have two main perspectives. On the one hand, we have the supervised one, in which we train a classifier to identify the abnormal samples and the normal samples by being trained on the basis of a labeled dataset with the annotations of normal and abnormal samples. What happens here is that Anomalies, by their very nature, are not likely to happen, so surely our classificator will be facing a really imbalanced classification problem, which is not easy to solve. And we have to take into account that raising a labeled dataset requires specialized knowledge about the domain that we are analyzing, and it takes a lot of time. So this supervised setting may not be feasible for all the cases in which we want to work. So there are other approaches which are based on unsupervised models, in which they are not trained on the basis of a labeled dataset for classifying anomalies and normal samples, but instead they are trained using only normal samples in their training set in order to capture the normality of the data distribution of the problem that we are facing. In these cases, our unsupervised model is trained using only normal samples, and once the model is trained in the test set, the model will be able to measure the abnormality degree or the anomaly score of each of the new samples. So if that abnormality degree or anomaly score is higher than a threshold, then we can infer that we are facing an anomaly. And a common approach for this is, for example, the autoencoder, which is an unsupervised approach, really common, really popular. So the autoencoder takes an input during the training, okay, takes a lot of input. By encoding that input, it computes the latent representations of the input in the latent space, and by decoding those latent representations, the input sample is reconstructed. So this autoencoder is trained by minimizing the reconstruction error between the input sample and the reconstructed sample. Once we have our autoencoder trained, we assume that the latent representations of the input samples capture the normal patterns and characteristics of our data distribution, and during the evaluation phase, for each of the samples in the test set, we compare the input of we compare the sample and the output of the model, and if the reconstruction error is higher than a threshold, then we can infer that we are facing an anomaly. So what happens with unsupervised approaches is that they tend to overfit to the normality of the samples that they have seen during the training phase. So we need to have a really diverse training set that covers all the whole normality of our data distribution, or otherwise, when in the evaluation set, when we have samples that slightly deviate from the normal patterns that we had in the training phase, these normal samples will be classified as anomalies. So in this case, the false positive rate increases, and this is not good. So there are different perspectives for overcoming this obstacle, and in this case, we are presenting self-supervised learning, which is a new unsupervised methodology in the field of machine learning. And this can be defined as predicting things that we already know about data in order to make our models capture the underlying structure and important patterns about the data distribution that we are facing in each problem. So the main elements of a self-supervised learning traditional framework are the downstream task, which is the main task, the main objective that we want to achieve, for example, a classification, or in our case, an anomaly detection, and the proxy task, which is the self-supervised task. The proxy task is commonly defined as an auxiliary task that we want to accomplish with our model, not because it's related to the main objective that we want to achieve, and indeed they are not related. We want our model to accomplish the proxy task because we assume that if the proxy task is well defined and it's accurate, we will be able to make our model learn good representations that will be beneficial for improving its performance in the final downstream task by accomplishing this proxy task. This can be done by making a pre-training using the proxy task, and afterwards using a fine-tuning methodology using the downstream objective, or we can jointly optimize both learning objectives. So finally, the aim of using self-supervised learning is to try to capture the underlying structure of the data distribution that we are facing for learning good representations of data that can improve the performance of our model in the final downstream task. by overcoming these struggles with generalization. So there are different kinds of self-supervised learning in the literature, and here we have one of the types of self-supervised learning, which is called self-predictive or augmentation-based self-supervised learning. In this case, for every pretext or proxy task in this field, during the training for each of the input samples, we apply a family of transformations to those input samples, and by those transformations, for each of the transformations, we generate an augmented view of the input samples of our training set. So once we have generated the augmented views, we can either try to predict which was the transformation that was applied to the original input sample to generate each of the augmented views by means of a self-supervised classification, or we can either try to reconstruct the original input sample on the basis of the augmented views. For example, imagine that we want to perform a classification of birds and cats images, and we want to apply a proxy task which is related to the self-predictive approach. So for each of the inputs in the training set, we apply a family of transformations, in this case related with rotation, and then we make our model perform a classification to predict which was the transformation that was applied to the input image to generate each of the augmented views by making a self-supervised classification. What we achieve by doing this is to make our model learn the semantics and the context of our data distribution and its instances, and that means that our model will be able to capture high-level features that will be beneficial for improving its performance in other tasks that are related with this data distribution. So some other common transformations, well, geometric transforms, as we have seen, masking part of the input and trying to reconstruct that input, and so on. And we also have contrastive self-supervised learning, in which in the pretext task, for each of the input samples in the training set, we apply a family of transformations, in this case rotations again, but here we do not try to predict which was the transformation that was applied to the input sample for generating each of the augmented views. In this case, we make an assumption about the context of the data distribution that we are facing. For example, if we apply a rotation to the input sample, we might assume that the augmented views and the input samples are similar. Then we might assume that we can learn good representations for the problems that are related with this data distribution by maximizing the similarity of the augmented views and the original input sample, and we might assume as well that this input sample and its augmented views is dissimilar with respect to other samples in the training set. So we maximize the similarity, that is, we pull together the representations of the augmented views with respect to the original sample, and we push away, that is, we minimize the similarity of the representations of the augmented views and the original sample and the other samples in the training set. So by this, if we use transformations that are complex enough, we will be able to identify or capture local patterns of the instances that will make that our model captures low-level features that will increase its performance in the problems that are related with this data distribution. So keep in mind that in the case of self-predictive, self-supervised learning, it's necessary to apply a transformation. But here in contrastive learning, and we will see an example later on, it's not that important to apply a transformation. Here we use the transformation to make the assumption that the augmented views and the input sample are similar. But we can make this assumption not by applying a transformation, but by assuming some similarities and dissimilarities of different parts of the data by having a specialized knowledge of the problem. We will see an example later on. So, a minute. As you have seen, well, these were the basic concepts of self-supervised learning in the field of images, because this methodology was firstly introduced in the artificial vision domain, And then the question is, how do we apply self-supervised learning to time series? This is not really trivial because, as we have seen, in many cases we use transformations. In the previous examples we were using rotation. Can we apply a rotation to a time series? Well, this means that there's a challenge here for applying self-supervised learning to another domain, and it means that we have to design specific transformations and specific proxy tasks that are related and rely on the domain that we are working with. So in the literature there are recent studies that were published like 3 years ago and 2 years ago and 1 year ago, I mean, that use self-supervised learning for performing anomaly detection in time series. And we have seen by reading all the papers that we have found in this domain that there are two main kinds of contributions. Ones that use a pure self-supervised learning approach, which is based on only using a self-supervised learning objective for performing the training of the model and the anomaly detection, and other approaches that use self-supervised learning as an auxiliary task for improving the performance of other unsupervised models as autoencoders. So, an example of pure self-supervised learning in the self-predictive domain is, for example, this contribution, which was carried out by some of the members of this research group, in which they wanted to identify anomalies related to the water distribution system of Chicago in order to find leakages in that water distribution system. So for training their model, their classificator, for each of the input samples, they applied a family of transformations based on increasing the flow of the water consumption of the people who lived in that particular city. So here, as you can see, they applied 4 transformations, one that was the identity of the original input sample, and another 3 transformations based on increasing more and more the flow of the time series. So finally, the aim of the classifier during the training phase was to try to predict which was the transformation applied to the input sample to generate each of the augmented views. So once they had trained their classifier in the inference phase, for each of the input samples in the test set, they applied these same transformations to each of the samples, generating the augmented views, and they tried to predict which was the transformation applied to the augmented views of the samples in the test set to check if those samples follow the normality that had been seen during the training phase. So after making the predictions, in this case, as we are only using a self-supervised learning objective for training our model, this was related with the final anomaly score that measured the abnormality degree of the samples in the test sample. So after making the predictions in the test sample, they detected anomalies by checking the misclassifications of the classifier with respect to predicting which was the transformation applied to the test sample for generating each of the augmented views. So they assumed that those misclassifications meant that the sample in which there were misclassifications didn't follow the normality that had been seen during the training phase. So this was their approach for detecting anomalies in a pure self-supervised learning way, by using a self-supervised classification. But there are other approaches in pure self-supervised learning in which the pretext task or the proxy task is not related with self-predictive self-supervised learning. This can be also related to contrastive learning for training the model. So in this case, for training their model for each of the input samples in the training set, they applied a combination of different transformations, for example, injecting noise to the time series, scaling it, permuting different windows in the time series, and they assumed that the original input sample and its augmentation was similar. and they assumed that the original input sample and the other samples in the training set were dissimilar. So they trained this model by maximizing the similarity using a Siamese neural network, by maximizing the similarity of the representations of the input sample and its augmented view, and minimizing, that is, pushing away the representations of the original input sample and the other samples in the training set. So once the model was trained, the inference was made by computing the latent representations of new test samples and computing the Frobenius distance between those representations and the mean of the latent representations of the samples in the training. So if that distance was higher than a threshold, they inferred that they were facing an anomaly. So as you can see, there's another kind of pure self-supervised learning in which the proxy task is not related with self-predictive self-supervised learning, but it's related with contrasting positive and negative pairs on the basis of the assumptions that we make about the similarity and the dissimilarity of different instances. And finally, we have another kind of approach in which self-supervised learning is combined with another unsupervised model, in this case with a gated recurrent unit-based autoencoder, for learning better representations. But in this case, the self-supervised learning objective is not related with the anomaly score, as self-supervised learning is introduced in this approach for getting better representations of data and improving the performance of the autoencoder, which is the main part that computes the anomaly score. So in this case, they were trying to detect anomalies in the Internet of Things field on the means of, by means of multivariate time series. So their approach was composed of three training objectives. On the one hand, the reconstruction loss, because we are using a recurrent unit-based autoencoder, and another loss based on trying to make a next step prediction on the basis of different windows for learning better representations. It doesn't matter. And finally, what's important here is that they used a loss based on contrasting different representations, and here they didn't use any kind of transformations. As I have said before, transformations can be applied in the contrastive learning framework for making assumptions about the similarity and the dissimilarity of different instances. But here they didn't apply any kind of transformations, and instead they assumed that the representations of the signals of the same sensor were similar. So they tried to maximize the representations, the latent representations of the signals that corresponded to the same sensor, and at the same time they tried to push away the representations of the signals of the sensors that were different, because they made this assumption and they used this loss for learning better representations. So finally, once the model was trained by using this multitask loss based on the three learning objectives, they used the autoencoder part for encoding and decoding each of the samples in the test set and computing the anomaly score by using the reconstruction error. So as you can see here, they just used an assumption about similarity and dissimilarity of parts of the data for trying to improve the performance of their model. So, después de esto, we are now working on a survey because there's no survey in this domain in the literature, and this methodology is really new for applying it. Self-supervised learning has been recently applied to time series anomaly detection for the last 3 years. So we plan to write a survey by proposing a taxonomy for classifying the different kinds of contributions based on the main characteristics of the contributions that we have found. Afterwards, we want to revisit the pretext tasks that are used in the field of self-supervised learning applied to time series domain, because we have said the transformations and pretext tasks rely and depend on the domain that we are applying them. And finally, we want to analyze the studies that have been published to propose some future work lines. So, issues and reflections. Everything related with self-supervised learning is a mess because there's no consensus about what are the types of self-supervised learning. There's no consensus about what's self-supervised learning because some authors say that using an autoencoder and making a reconstruction objective is self-supervised learning. Some others say it's not. Some others say making next step prediction is self-supervised learning. Some others say it's not. So we are finally going crazy. We are just trying our best. And I hope that by next year I will come with better news. So thank you so much for your attention. And if you have any kind of questions, just ask. I will try my best to answer them. Thank you.
Thank you, Aitor. It was a great talk. Any questions here?
One class. You first. I think you just mentioned that not all the papers that you review assume that all the samples are of normal class. It was not clear for me that in this review part, all the papers, all the works assume that all your sample, your instances belong to a normal class, or is your training sample corrupted by normal samples? And the second question, are those non-normal samples are also labeled? Or it depends on the application, it depends on the paper, or?
Okay, in every paper that we have found, they assume that the training set is based only on normal samples. There are some contributions that make a reflection about the struggling that have unsupervised approaches for anomaly detection when there's a sample contamination that is having abnormalities in the training set. And they think that self-supervised learning can be robust to that contamination, but in the contributions that we have found, they assume that all the training set is composed by normal samples.
And I thought when applying those transformations, I think that all the samples that you have seen in the slides, they are related to images. And of course, no, if you, for example, no, this image or the image of the cat, no, if you have an image sample, if you apply a transformation, you have a parrot, you have a cat, and if you apply a transformation, you continue having a cat, you continue having a parrot, no, moving in this way, in horizontal, yes, diagonal, moving the angle, and so on. And all those transformations are based in an spatio assumption that also the cat continues being there. It doesn't matter what transformation do you apply. But does the same idea apply for time series? If you apply a transformation to a time series, can you trust? Because you have proposed several ideas. No, I can apply several transformations to my time series. But are you sure about the assumption that after applying that transformation to a time series, the time series continues being of the same class of the non-transformed one?
No, of course not. But when you are doing anomaly detection, you are, yeah, it's a really good question. The thing is that you can apply transformations that make imagine you have a problem with noise. So you want to make your model be robust to noise. So you can define a transformation based on injecting Gaussian noise and assume that the representations, for example, in a contrastive learning setting, the representations of as the time series after injecting that noise is still a normal samples, you can try to push pull together the representations of those samples to try to make your model be robust to noise. But for example, you can make imagine that scaling a time series in a context makes the time series become abnormal. Then the thing is that the assumption that you have to make is that these are not similar samples anymore, so you want to push them away. It depends. I mean, this kind of approaches rely heavily in the kind of transformations that you apply and the kind of assumptions that you finally make about the similarities and the dissimilarities. For example, in the case of uncontrastive learning. So it depends on you. So there are several studies that are trying to overcome this little obstacle, this dependence with respect to the context of the problem, this dependence with this necessity to design specific transformations to each of the problems. But I mean, it depends on the assumptions that you make. Did I answer your question, Iñaki?
It's true, no, that all the time that you put the example of the images, no, and of course, no, we understand that applying a transformation to image, the image continues having the same object, no?
Yeah, but
for time series, wow.
For example, here in this contribution, the applied transformations that are based on increasing the flow of the measurements of the time series for detecting leakages. This is a transformation that is directly related to anomalies, because if you increase the flow, then surely you can imagine that maybe there's an anomaly in there. So by using a self-supervised classification, if you have misclassifications in this kind of transformations, then you can assume that you are having an anomaly. So as you can see here, the transformation is related to making the normal samples look abnormal, but their model is robust to find anomalies as well, even if the transformation makes the normal samples look abnormal. And indeed, I think that's the aim, to make the normal samples look abnormal and try to measure or try to predict which is the behavior of the normal class after transforming it. Yes?
Okay, thank you, Aitor. Very interesting talk. I didn't know that there were so many things about, so I haven't followed self-supervised learning so much in the past few years. And the first question was, are there a lot of papers like to do a survey?
There are well, first, the thing is that when we made the first look for the papers, we found 60. We discarded 40. Because they were saying that they were using self-supervised learning, and it wasn't like that. But finally, by looking at the references, the citations and stuff, we found 50, 60 maybe. So it's not easy, because we cannot rely only on the name of the contribution, because some people say that they are using self-supervised learning and they are not, and the other way around. So by looking for the references and the citations and analyzing the methods that they are using, we can extract more papers. So we have 40, 50, 60.
Another, well, I have one question that is a bit related to, I mean, you haven't really, well, at the beginning you talked about anomaly detection in time series, and you saw that it's a complex problem with a lot of types of anomalies. But then the self-supervised problems that are available in the literature, are they useful for all of them, or are they very specific for one type of, because for example in our case it was very specific for one type of anomaly.
Yeah, the thing is, in this contribution, which was
Yes.
carried out by them, found subsequence outliers, and it's the more general case, because for contrasting the context, you somehow need to use a window. For example, using windows you can find mainly subsequences, and you can find the whole time series that are...
For points, I'm thinking that it's more...
There are methods, but they are not many. But there are some, because they use autoregressive methods for computing the anomaly score of a point on the basis of the context of the window that comes until that point, but those are like 3 or 4. So we don't plan to include the type of anomalies that they identify in the taxonomy, because it would be so messy.
And then the last question is, well, I have more, but I will leave you alone. And I think that one of the most difficult things of self-supervised learning is that, and especially in the area of time series, the transformations are difficult to define. And is it always the case that the transformations are very ad hoc and very related to the problem at hand?
No, there are some contributions, a few contributions that propose transformations which are not really ad hoc to the context of the problem. For example, permutating different windows of a time series for classifying if there was a permutation of one type of another type and stuff, that's independent to the context, or changing the resolution of time series, or masking part of the time series. Those are not that ad hoc. And the thing is that in this case, these kind of transformations are used in self-predictive, self-supervised learning, because you have to try to make complex enough transformations to learn good representations, but if they are so complex, then your classifier won't be able to identify which was the transformation applied, so maybe it fails. So in the case of contrastive learning, for example, contrastive learning is not that dependent on the transformation that you apply, because it's as simple as combining so many transformations for making a really complex augmented view, and try to pull together those representations, even if the images or the time series in this case are so dissimilar by seeing them.
But the thing is that if your augmented view, I mean, in all the cases, in the end, what you do is you have a new sample, which is an anomaly, and you identify that it's an anomaly because it's different. Its transformations are different to those of the normal samples. That's the main idea. The thing is that if those transformations aren't really related to the type of anomaly that you have, when you introduce the anomaly, you won't be able to detect that it's...
Yeah.
No? It does have to be somehow related to...
That's exclusively the case of self-predictive, self-supervised learning, because if the transformation is not related to the kind of anomaly or to the context, then the behavior of a normal sample and the abnormal sample, when you apply the transformation, might be the same, so you are not capturing that difference. But, well, yeah, so that's why self-predictive has been like replaced by contrastive learning mainly. Yeah.
Okay. Thank you very much, Aitor.
It seems like there's a common issue of proposing the transformations that are suitable for the problem. And are there any works that try to avoid using transformations, like, for example, predicting the next element in the sequence?
Yeah, there are, but we don't think that, well, there is an issue with if that's self-supervised learning or it's not. Another clear example in contrastive learning, for example, can be, as I have mentioned before, in this case, they assume that, imagine that you have 4 sensors and you have different time series with measurements of those 4 sensors. So you assume, you don't apply any kind of transformations, and you assume that the measurements of the same sensor in 2 different time series are similar. So you pull together those, for example. Normally in self-predictive, you need to apply transformations, or otherwise you go to the issue that you do not know if they are just using an unsupervised approach or they are using an unsupervised and self-supervised approach, because the line between them, it's not clear.
I have a question also. As Mikel said, there is this option that you have a time series. You could mask some part of the time series and try to predict.
Of course.
That's I think that's the same as it's done in NLP, in natural language processing, where you have a phrase and you mask, and it's called self-supervised learning. Why do you say that it's maybe not here?
No. Masking and reconstructing is self-supervised learning because you are applying a transformation. But what I mean is well, for example, is an autoencoder a self-supervised learning approach? You are trying to predict which is the original sample on the basis of a latent representation that has not the same dimensionality as the input sample, so you have lost information. Is that a kind of masking? I mean, it's like, but masking is considered a self-supervised learning, and as I have said before, it's considered a kind of self-predictive, self-supervised learning. Then we have our doubts about considering next step prediction, for example, as Mikel proposed, self-supervised learning, because there are some authors that say it's not, and there are some papers in NIPS that say it is, and there are some papers in AAAI that say it's not, and I'm not the person that goes and says, well, this is not. So we will see.
Okay, thank you. Okay, so thank you, Aitor. It was a great talk.
Thank you.